it's completely feasible that you won't have programming languages.
This is Roberto, the creator of the Lua programming language, and I asked him all about programming language design.
C++, I think, is a good example of a language that it's really, really complex. JavaScript, I think, is even worse. I always joke that the JavaScript, the good part, is a very thin book compared with the official JavaScript books.
Given how much AI has been progressing, would you still recommend people learn computer science today?
If you really think about that, it's really difficult to recommend people learning anything.
Here's the full episode. In 2023, Lua was the second highest programming language by growth, according to contributors on GitHub. And I saw that it was also used in famous games like World of Warcraft and Roblox. And so I wanted to ask you, what kind of programming language is Lua and what sets it apart?
Lua is a language that usually you use together, combined with another language like C or C++. And then you have an architecture where Lua takes care of the more dynamic part of your program, things that change more frequently, things that are not so resource intensive. The hard parts you have written in C or C++. So it's typically what is called a scripting language. There is some confusion, I think, between scripting languages and dynamic languages. And people just, I think, consider a dynamic language to be more or less the same thing as a scripting language. And they are not exactly the same thing. So, for instance, a big difference between Lua and several other scripting languages is that for scripting, you have two typical uses. You can have the that I call who has the main loop. So you can have the program written in C and calling Lua, or you have your program written in Lua calling C. And for several called scripting languages are actually, you don't have to, but it's much more easy to use if you have your program written in the scripting language and the C language is only for your libraries. And Lua, it's very good fit when you want the reverse. You want the program written in C, and then you have, it calls Lua from time to time. So the point is that Lua, it's very good at this, that you have the main loop, the program written in C, and then it calls Lua for some tasks or for whatever you want to do. And for instance, in games, this is very important to keep the frame ratio of the game. So for instance, you have the loop keeps the rhythm of the game and keeps everything. And then at every frame, it calls Lua. Lua's updates all characters, all images, everything in the game. And then it returns to C to do the renderization, etc. So it is a very good fit. But the main point is that the people sometimes call this the embedding versus extending. So you can extend the scripting language with C, or you can embed the scripting language into C. And so several languages are very good only for extending, while Lua it's really good for both embedding and extending.
Why is Lua good for embedding? And Python, it's almost the opposite.
Because Lua, since the beginning, we thought about Lua as a library. Since the beginning, Lua was written as a library. So I think that's the main difference. Lua has a standalone program that, I mean, you can call Lua in your console, in your command line. But that program is just a client of the official client of the library, following the same API that any other program can use. So this idea of language as a library, I think it's not very common. It's something that is very particular in Lua.
When you design a language as a library, what are the unique, I guess, design decisions?
I think that goes a lot of small and big details. For instance, your idea of what is your global space, or about scopes of variables, about exception handling, for instance. It's very important that it's very common in Lua that you raise an exception in Lua, but you catch the exception in C. So all these things about how you do exception handling in the language. Another, it's not a big deal, but it's, for instance, most dynamic languages, that's almost a definition of a dynamic language. They have an eval function that you can give a piece of code and then it executes that code. In Lua, we don't, instead of eval, we have a function that we call load, that you give a piece of code and it returns a function, an internal function, like it was a Lua function, that when you call that function, then you execute the associated code. It doesn't execute immediately. So you have this clear separation between compiling like the Lua code that you have, and then you can do that in C. So in C you can get a piece of Lua code, you can compile it, check if it has errors, etc. Then you call that for instance, a different piece, or you can even call several times. For instance, you can load functions from Lua into C. You keep them, in the Lua space, and then you can call that same function again and again. It's not a big difference, of course, because if you have eval, you can evaluate a function declaration and then returns that function. So you can, if you have eval, you can do load. If you have load, you can do eval. But I think load, it's simpler to use for that kind of thing. That is when you think about libraries, for instance. In Lua, it doesn't have a global state. I think that's I forgot that's a very important difference. When C starts, the first thing it has to do is to create a new Lua state. And then everything you do on that state, and that state is completely independent of everything else. So C can, for instance, create another Lua state, and both states are completely independent, there is no communication between them. And so this again shows that, and so for instance, C can use a state, do a lot of stuff, and then it can close the state, and all memory used by Lua is released. Everything that Lua was using is released. And for instance, if C doesn't need to use Lua anymore for a program, you release all resources used by Lua, and your program in C continues. And then later it can again create another state, etc. So there's, as I said, there is several small or not so small decisions in the language, but all the time we think about the language as, is that good for embedding? Is that possible to do embedding and things like that?
When you think of the programming community generally, everyone is quite familiar with Python, but not as familiar with Lua. I thought it might be interesting to compare the two languages. So if you compared Lua to Python, what are the pros and cons of each language design?
Lua is a language that is intended to be used in this idea of scripting architecture. So the Lua, for instance, it doesn't thrive having a lot of different libraries. If you have something that, I want to write a quick program for something, that Python is much better. It has all the libraries, you can dream about it. It has a lot of libraries built in already into the language. So the language is huge. The installation, it's a huge download, etc. But it has exactly, I need that, it's there. I need that, it's there. And Lua is almost the opposite. It's a very minimalistic language, because the idea is that you embed Lua into your program. It doesn't use almost any resources. Most of the libraries, the important libraries that you will use, will be provided by the program itself, will be the commands like move a character or do some speech or things like that from the engine of the game. For instance, if you think about games, but whatever it is. So Lua, I think that's the main big difference. It's that they have very different goals.
I saw some benchmarks and I saw that Lua is much faster than Python. Why is that?
Those benchmarks are not exactly, but I think that the main point is exactly, one thing is that Lua does have this focus on performance, again, in the realm of scripting languages, doesn't want to compete with C or C++, but in the realm of dynamic, mostly now it's dynamic language, not scripting languages, we have some focus on performance. So I think this is a first difference. Python exactly is much more, I think it's a decision that they make. Performance is not that important. It's more important to be flexible, to be easy to do whatever you want to do. Then in Lua, sometimes we do not put some features because we think that there is no way to implement that efficiently. But also, I think some part of the performance difference comes exactly because of the size of Lua. So most of the virtual machine fits in your cache, for instance. I think there is these two big things. One is that Lua doesn't have so many features. It's not so dynamic as Python. So in Python, there is a lot of indirections because everything can mean something else. In Lua, we are a little more conservative on that side. But I think also this thing of being small also makes it naturally faster.
So on the distinction between scripting languages and dynamic, or I guess it seems like dynamic language is a superset, scripting language is a subset of that. Am I understanding that JavaScript is a dynamic language, not a scripting language from your perspective?
Yes, exactly. Yes, exactly. Because the scripting, it came, the original scripting language was Bash, or the shells from Unix, of this idea that there is a language that coordinates other stuff. So for instance, it can be extending, again, you can use, but this idea that you have two different languages, for instance, the shell is only useful because you have a lot of programs written in C that are controlled by shell. So the scripting language has this very strong idea that you have this idea of a dual language architecture. So scripting is like, it's the name scripting, it means it's like you coordinate or you give a script to be executed by those other things.
You gave a talk a while ago and someone asked you a question of, what books do you recommend for, studying programming languages? And you said actually that you enjoyed studying the language design of other programming languages.
I like reading books that describe the design of the languages. I think the best books are those written by the author of a language about the design of that language.
What book recommendation do you think is best on language design?
JavaScript, The Good Parts, for instance. It's kind of old now, but I think it's a very interesting book. Although I always joke that the JavaScript, The Good Part, a very thin book compared with the official JavaScript books, like 1/10 of the language is the good parts. But I think that book is really interesting, because exactly it discusses the language, it discusses even the bad parts, and it focuses on the good parts, but then explains why it's there, why it was made that way, etc. That is a book that I like.
When we were talking about Lua, it sounds like one of the things that sets Lua apart is the performance and how minimal it is. And when I was reading about Lua, I saw that there's LuaJIT. How does the LuaJIT work?
LuaJIT, the first thing, it's a completely different project. It doesn't have anything to do with us, but it's an incredible piece of software that is a just-in-time compiler for Lua. And I think exactly one of the reasons it works so well on top of Lua is because of the simplicity of Lua. It's a very regular language. I mean, it has a very, as I said, it doesn't have many exceptions or too many indirections or things that, so it's not that dynamic. I mean, everything can mean something completely different. So that, I think that gives a very good language for a JIT. But the Mike Paul is the name of the guy that made I think he's still working on that, on the first Logit. It's unbelievable, his work.
What makes writing a JIT difficult?
The first thing that, for me, I don't want to get involved with JIT is because it's machine dependent. It's not very productive. I mean, you do a lot of work on it, only works on that architecture, and then, oh, I want to run in another architecture. But Mike Paul, he created a kind of a pseudo assembler that he writes in this assembly, and then he translates that assembler to real machine code of the different machines, so trying to unify the different architectures. So there is a lot of work, but I don't like it. I think architecture, I like to study, but I don't like to work with, because I think it's very unstable. Each new version, they change that or they change that. They change the ADI for something, and then now the stack has to be aligned in some very particular way. And so, and of course, also to get that performance that he gets, he made what's called a trace compiler. The idea of a trace compiler, that instead of getting a function and compiling a function, it works like any JIT, that it tries to detect things that are executed frequently. And so it starts what's called a trace. It gets recording everything that the code is doing, including function calls, etc., until it closes the loop. And then it compiles that loop, including function calls, etc., everything in line. It compiles that for that specific, for instance, so that number happens to be an integer, so it compiles f, the number will be an integer again, and there is a lot of checks, just check if everything is as assumed, and then it executes the loop. And then it's very, very, very fast. But anything that is different, for instance, you call again that, but you call it frequently with integers, suddenly you call to with a float, then at some part of the code it breaks the condition, and you have to return to the interpreter part. And I think that's one of the worst parts, is that you have to translate the state, that it's all compressed into registers, etc. For instance, you don't even have a call stack because you didn't do the calls, you just inlined it. But then, oops, something went wrong. Now you have to continue interpreting. So you have to recreate the stack that you didn't create originally, etc. So I mean, even to think about that, I have headaches.
Standard Lua is portable, but to execute on a machine, it eventually gets converted into machine instructions somewhere. Where in the stack is it eventually translated to machine instructions?
Lua is written in C, the interpreter is written in C, and then you compile that into machine code, the interpreter, the Lua code. Then when you get the Lua interpreter code, when you get some Lua code, you do what we call a pre-compilation. That is, we translate to an internal language, and then the interpreter is just a big loop. It's a loop with a switch. I mean, that's a very big simplification, but in general terms, a loop with a switch that gets instruction, does a switch, and see, oh, this instruction the instructions are quite similar to a CPU. Move that, but then instead of creating, it executes that instruction. Move A to B. So it does a move A to B and executes that, and again repeats execute the next instruction. So this is how an interpreter works. And basically, so we pre-compile Lua. There is a compilation, but we compile for this virtual machine. And then we have this main interpreter loop that people call that just fetch it instruction. So a jump is just a jump. You have an array of byte codes. A jump will just go to that. You have a counter that tells where you are in this array. A jump, you just update that counter. It goes to another position of that array where you're going to. So it's like you emulate the CPU in software. It's written in C, the interpreter. This main loop is written in C. So if you compile it in Linux, it will run in Linux or in a x86 architecture, it will run in that architecture. If you compile that in the Mac, it will run in the Mac. It's a C program.
Got it. Okay. So, and that's the part that's not portable, and the C compiler handles that.
Yes. All portability of Lua comes on top of portability of C.
How does JIT compare to ahead of time compilation in terms of performance?
Both ahead of time, any kind of compilation is not easily, but it can be 10 times faster than interpreting, or even 100 times faster than interpreting, depending what you are doing. But 10 times is a very good figure. Between ahead of time and trace compilation, then depends a lot of what you are doing. After trace compilation is particularly good for benchmarks, because you're repeating it more or less. They are very uniform. You are doing exactly the same thing again and again and again. So then trace compilers shine. This is the best they can do. In real programs, that's depends a lot, but I wouldn't say there is a clear winner between the two. I think depends a lot of the kind of program.
Is it possible to write an ahead of time compiler for Lua?
Yes, there are several. None. I'm not sure if there is anyone on production quality, but for research, etc., there are several. I have a student who wrote one, like a master thesis, ridiculous simple Lua compiler, ahead of time Lua compiler, or something like that. Exactly, because it was just, it gets these opcodes and expands into C code, and then you send that through a C compiler, and then you have a head of time compiler for Lua, and it gave like 3-5 times boost in performance. It's very, very, as the title said, it's like ridiculous simple compiler.
I always hear there's compiled languages and there's dynamic or interpreted languages, I guess. But really that distinction is in the toolchain, not necessarily in the way that the symbols are laid out on the source code. Like I could write a compiler or a program that takes in Python code and then converts it into machine code, and then I would have compiled Python.
And you can interpret C code too. You can write an interpreter for C. Yes. But the main difference is exactly what it's easy to do. For instance, as I said, one of the hallmarks of interpreted language is the eval. So if you want to compile the language and keep eval, you have to have a compiler as a library of your runtime, because you may want to compile things during execution. This is the hallmark of a dynamic language. So you can create code while running code. So that part is that's why much more often than not, dynamic languages are interpreted. But you can compile, but then sometimes, for some compilers do not handle eval at all. They say, oh, you can compile as long as your program doesn't have evals. So there is some restrictions. And as I said, you can interpret C code, but you'll be extremely slowly. It doesn't, but
I think one big difference, and when I look at static languages or compiled languages, they seem to have type systems in them, or the type annotations. What is the role of a type system in the compilation process?
depends a lot on the type system. Several type systems, like in C, for instance, are written to be a very important part of the compilation process. So if you have the right type system, it's much, much easier to write a compiler. A trivial example is the space for variables, because if you know, oh, this is an integer, this is a float, this is a double, you know exactly how many bytes of memory you need to that. Otherwise, it's a mess. More often than not, you have to keep everything in the heap, dynamically allocated, and so huge penalty in performance. And for instance, when you see, as I said, a trivial, you have an addition, A plus B. If you know the type of A plus B, you have the type of A, the type of B, you have at compile time, you know, oh, this plus is I'm adding two integers, I just generate the machine code to add integers, and there everything is fine. In a dynamic language, I say a plus, I compile to in the virtual language is just piece of plus, but then how do at runtime you have to check what is A, oh, A is an integer, B is a float, oh, I have to convert, or B is a string, or depending on the language, if you're not doing addition, you can be doing concatenation, or you can just calling some, and you have to do all that at runtime. So types can be very, very important to compile efficiently, but of course you have to have a type system that there are several languages now, like TypeScript, that the types are kind of, you do not guarantee that everything has the types you said they have. So then it's impossible to use them to compile, because, oh, probably A will be an integer, but if it's not, I have an integer register to boot to A must be a register, or things will not work. So, but if you have the right type system, they are essential for a good compilation.
I know some programming languages have type inference. What if you ran type inference and you got an unambiguous set of types, and then you use that in compilation? Like, could you do that for Lua?
No. That's not computable, but a lot of people try to do type inference for dynamic languages, and it's really hard problem, and it's very difficult to do anything useful in terms of performance. What sometimes you get, but you have a very restrict, if you write your program in that specific way, follow. So it's like you don't have the type, but you write the program thinking about types. And then if the program is that very particular format, then you can do type inference and everything goes well. Otherwise, either type inference doesn't work, or, it works, but it infers very generic types for everything, and so you cannot take advantage of the types. Because exactly the dynamic nature of the language, this also happens with Logit, for instance. You can get much, much better performance if you have a kind of a type system in your mind. Usually we do that, and you follow that type rules even without, the compiler, the language does not impose them on you, but you assume, oh, I'm going to follow those, some time discipline. I'm not going to use the same variable to store integers and strings, etc. And then you can have much better results.
OpenAI, Anthropic, Cursor, and Vercel all use this product to make their lives better. And the problem it solves is when you're building SaaS or an AI product and you want to sell to other companies, there's all these requirements you need to meet. There's SSO, there's SCIM, there's RBAC, there's audit logs. These are all things that take time to integrate, but aren't the main focus of your app. WorkOS is an API layer that lets you meet all of these requirements in just a few lines of code. So let's say you have a new SaaS product and you want to sell to other companies. WorkOS will solve all of these critical feature gaps for you. You can check them out at workos.com to learn more and get started. And I appreciate them for supporting my work and sponsoring this podcast. Earlier, you mentioned that Lua can call C and C could call Lua. And you mentioned, we talked about the compiler and the interpreter, and how do these pieces work together in the case where you're chaining different programming languages?
Yeah, the main trick, I mean, it's not a trick, the technique for Lua calling C is C pointers, function pointers. There is a pointer to a function. This is part of the official C language. So when you start Lua, suppose you are in C, yeah, as I said, you create a library, you create a state, a Lua state, and then you can register, you send to Lua C pointers, function pointers, I mean pointers to functions in your C library, associated with names. Lua stores that in some data structure. Okay, so it says, oh, the function sign is associated with that pointer, etc. So when it's doing the interpretation, oh, this instruction is call, instruction called. Oh, let's see what it's calling. Oh, it's calling A. What is the value of A? Oh, it's a pointer to, and then it calls that pointer. And then we did call the C function to do that. And when C wants to call Lua, I mean, a Lua function is just a data structure from the point of view of C. It's just an array of byte codes, of opcodes. And then it calls the Lua interpreter function. Please interpret that function for me. So C can call Lua to interpret that function, and that function is running, and then can call a C function using a pointer. And you can have that in the stack at several levels. So we are running a Lua function that calls C, and C calls Lua again, and Lua calls C, and you have recursive stuff in that, etc., and everything works. It just works.
In one of your talks on Lua, you mentioned that there's security benefits to using a scripting language. Well, what are those benefits, and how does it protect the hardware?
It's not only hardware. Once I gave a talk here in Brazil. I was called to give a talk in a conference, a PyCon, they call it a Python conference in Brazil. They called me for a talk. At the end of the talk, I said, oh, let's use it as a scripting language. As I said, emphasizing that thing that you have this dual language architecture. And I know of cases of Lua being used with C, with C++, with Fortran, with several different languages. And then someone in the audience says, oh, we also use Lua for scripting Python programs. And what's the case? They have a huge Python program for financial stuff that do a lot of financial transactions, etc. And they wanted to do script, I mean, to have a command line where you could write instructions to be executed by at runtime, for instance, for debugging or for inspecting, for whatever you need, some kind of end-user programming. But they said exactly what I was talking about, spaces. In Python, basically, if you have a command line and you are going to run Python, that Python can do whatever it wants to do in your program. There is no way to protect it. So if you gave that to the user could do whatever it wanted to do, I mean, for the program. And so the program would break a lot of invariants of a lot of important stuff in the files it kept, etc. And so what they did, they gave the thing in Lua, because as I said, Lua, you create a state. For instance, as I just mentioned, You can only call C functions. That is true in Python again, but in that particular case. You can only call C functions if you give the C pointer to Lua. So you have a very strict, and there is very, as I said, there is a library. When you create a Lua state, it has no functions at all. There is nothing, I mean, you cannot open files. Everything there are, we call standard libraries. Usually you open a state and you register those standard libraries in Lua, so you have the minimum, like you have mathematical functions, etc. But you can open a state and register no functions at all in Lua. It can only do things calling those specific functions you gave. So they use Lua to have this kind of control. Or you can write Lua code here, but that Lua code can only do very specific things in the Python program. You cannot call any Python function or, I mean, build any kind of Python data structure, etc. So was this a nice example? In the case of hardware, it's the same thing. You cannot just go in, for instance, there is a port, a hardware port, that controls the speed of the fan, that keeps the temperature of the CPU. And if you put that very low, you can really burn the CPU, I mean, because the CPU gets very hot. And so if you have a C, you cannot call C directly. You must call Lua, and only Lua has access to that. So if you can only program in Lua, it's, Lua, then you check whether the numbers you are giving are precise or whatever it has to check, and then it calls.
It's kind of like a sandbox environment.
Yes, exactly. Yes, sandbox is the exact word for that.
I saw there was this, I guess, paper, or maybe it was a article you wrote on the history of Lua with several other people, and I thought there were some interesting quotes in there I kind of wanted to ask you about. So one of them, it says that there's this old joke that says that a camel is a horse designed by a committee.
Yes, that's not mine. That's a real old joke.
Does that mean that you think the best programming languages are designed by as few people as possible?
Yes, I do think, yes. Because one thing that it's easy to observe is this. If you have a committee writing a language, everyone wants to put something from themselves into the language. So you have that, your favorite mechanism, and you will fight whatever it takes to put your favorite mechanism into the language. And very few people will fight against putting anything in the language. I mean, some people say, oh no, this is too much, this is too complicated, but people fight much more fiercely for put something they want in the language than against putting something in the language. So when you have a committee, the tendency is, oh, let's keep adding stuff, and people sometimes even do not understand. I mean, you're not sure if everybody there is really know the language well. I'm putting that, but that fits with other parts of the, I didn't even know the language has this other part. I mean, so things sometimes do not fit together very well, etc. So first you have what's called the conceptual integrity. It's a name that gives that everything fits together, everything, it's designed with everything else in mind, etc. It's much easier to, I'm not saying, I mean, Lua has several wrong stuff regarding, because with time, etc., there you make mistakes. But it's much easier to get things right if you have a small group of people that everybody knows what everybody else is thinking. I mean, you are deciding whether to put something in the language or not. It's much easier to change your mind if you do not put something and then later you decide to add it to the language, than to add something and then later you decide, oh, I shouldn't have. But that was not a good idea. So when in doubt, our default is always don't put it. If you're not very sure, don't put it. We can always add that later, and so keep the door open to change your mind.
I saw in the original Lua programming language that there was no Boolean type, and I've never seen that before. Why was there no Boolean in the original Lua?
Well, C doesn't have Booleans. I mean, the original C and C90 up to C99 use integers. If it's 0, it's false. If it's different from 0, it's true. And people lived quite well with that. Lisp. And there are several languages that don't have Booleans. And actually, we only put Booleans in Lua because we wanted false. True is completely useless in Lua. Nobody uses true. I mean, nobody is a joke, but it's too strong. But it's not very useful. You can use almost any other value for true. But the problem is that in Lua, the nil, that special value, nil, is in a table. It is equivalent to the key not being present. You always think whether that was a good decision, but it's very embedded in the design of the language. And it has this strong concept that a table, a key that is not present in a table, there is an associative array, it has a nil value. It's completely indistinguishable whether it's absent. I mean, absent means it has a nil value, nil value means it's absent. And so sometimes you want to have a false value, but you want to know, oh, it is there in the table, and so we needed a false to have. A false you can put in the table, and it's completely different from being absent. You know, there is a key, and the key has a false value. So we needed a false value, and if you're going to have a false, then we added true. It would make sense to have false without true, but with true it's almost useless.
Why not use 0 as false if you're okay with 1 as true?
We could have used it, but that, among other things, that would be a big change, because exactly it was that way. So we added that later in the language. So changing 0 to false would be a very big incompatibility. But it could be, for instance, in Python, I think a lot of stuff are false. I mean, 0 is false, empty list is false, empty. In JavaScript, I think it's even worse. I don't recall exactly, but I mean, this is kind of arbitrary. I mean, we could have, for instance, nil, false, 0, empty string. I mean, it just depends the kind of test that you use. It's not in dynamic languages, it's very easy.
Python has like you're describing, the truthy values and the falsy values, or I guess they can be interpreted as false. But it's more implicit, less explicit. And I know JavaScript is even further on that spectrum, where you can do some really weird stuff that implicitly has some behavior. Do you think that design direction is good or bad?
It's like it's more compact, it's more easy to write stuff, but you always have this balance in any languages, almost anything. The more flexible the more flexibility you have, the less protection you have. In C, you have something like that. People do not notice, but because C is typed. But you can check whether an integer is true or false. You can check whether a float is true or false directly, because again, it checks whether the float is 0 or different from 0. You can check whether a pointer is null or different from null, because in C, null is a magic 0. So it's kind of, if you do not write any test, it has an implicit test like different from 0. And this 0 can be an integer, can be a float, can be a pointer. So in C also you have this kind of flexibility. It's just that you have to be more explicit. Usually this avoids errors, but so this you have always this balance between easy to write and easy to make mistakes.
I saw that Lua is 1 indexed instead of 0 indexed, and I had never seen a programming language like that in my experience.
There was a lot of programming languages like that.
So yeah, why is it 1 indexed?
Because everything in the real world are 1 indexed. If you have a book, you have the chapter 1, chapter 2, nobody number chapters as 0, 1, 2, 3. Only programmers are the only, even mathematicians, if you get a mathematic book, a book of mathematics, any sequence, it's A1 and A2, A3. If you get a matrix, the first element is A11, A12, and then everything is written with 1. Only in programming language there is this idea of 0. And the funniest part is that, for instance, Fortran, that now it's very old language, but index it from 1. In Pascal, you can choose. You write an array, you can say this array is indexed from -5 to 5. And so it's indexed from whatever value you want to whatever value you want. 0 became extremely popular because of C. C used 0, and a lot of languages copied, are kind of inspired by C. They have the same operators, the same syntax for expressions, the Boolean operators, for instance, that is not standard mathematics. Almost all languages chose the same operators as they are written in C. And so a lot of languages copied C, and then 0 indexed became very popular. And what is funny is that in C, there is no indexing. In C, indexing is just an illusion, because what you have is pointer arithmetic. And see, when you write A indexed by I, actually what you are saying, get the contents of A plus Y. And so, because in C you don't have indexing, you have this displacements or deltas, I don't know how, offsets, then it must have indexed by 0 because then the first element is the element that is at the original address. So C doesn't have indexing. So when you say A is indexed by 0, it doesn't index by 0 because it doesn't index by anything. But it has this illusion of indexing, and then it's easy to think that it. And then a lot of languages that do not use pointer arithmetic, do not have this restriction, do not have this semantics, copied C and kept the 0 indexing as the thing. If you get a 12-year-old and try to explain to them the 0 indexing, I assure it's much, much easier for them to write, I have a list of the first element. I always joke that the first element is 0. And you write first for 1, but the first element 1 is not 1, it's 0. So it has advantages, 0. For instance, for some specific operators, mathematically, for instance, you want to do a circular buffer, 0 is better. There are some small advantage, but it's much, much more confusing. And as Lua has this idea of end-user programming, we always joke it's much easier to make life easier for the non-programmers. And I am sure that programmers can program whatever index they have to do, because they are supposedly they are professional. They can learn that indexing from then to put on the end user the burden of using something completely different from them, indexing by 0. What does it mean, the element index 0? I never saw, the chapters in the book. Yes, the first chapter is at 0, the second chapter is at 1. No, I'm not joking. When you try to explain that to non-programmers, even don't, Doesn't need to be 12-year-olds. I mean, just get anyone that is not. And then programmers think, oh, I have the absolute. I mean, but you are grown up. I mean, okay, you are accustomed. You are with zero. I'm sure you can learn to program with 1 or -1 or whatever it is, the base you have to use, I'm sure.
But do you think you see a lot of bugs because maybe someone thinks it's 0?
Unfortunately, I see some bugs, but as I always say, that's are the kind of bugs that just shows that you didn't do minimum testing. Because that kind of bug is not a kind of that kind of bug that, oh, if you tried anything you try to do in an array, if you start from 0 or start from 1, you have a bug. So the most simple test that you can imagine to test anything related to an array, to a list, etc. And if you mistake 0 to 1, you detect that. So if you have that kind of bug, it just shows that you didn't test that code at all.
There was this talk that you gave on the cost of adding language features to Lua and how there's a lot of hidden costs. And I think today, implementation costs of software is going down due to AI code generation or LLMs. And I was wondering if that changes your thinking on, I guess, the cost of adding features to a programming language.
AI is something that we don't really know what is going to happen. If you go to an extreme, it's completely feasible that we won't have programming languages. And I mean, because if the AI is writing all your code and is checking all your code and doing everything, in a few years, maybe we don't need programming. AI can write machine code directly. It doesn't need programming languages. It's easier for them to compile or even generate the code directly. I mean, I don't know what's going to happen in a few years. So I think it's very hard for me to talk anything about AI because I think nobody have a clear idea people have maybe a clear idea what it happens in 1 year or 2 years, but in 5 years, I mean, anyone that says, oh, that's going to happen in 5 years, it's just, just guess. So I think it's hard to say anything. This is all because of AI. So keeping the minimum thing, that you still have, for instance, why you still use programming languages? Because you want the user or some human to be able to check the result of what the AI is doing, etc. So I still think that most of the things about programming language still hold. For instance, the cost of complexity of you understanding. AI create a code for you, and then you really understanding what that code does. It's even worse. It's much more important that the language be clear and it has no hidden mechanisms, because the AI may use a hidden mechanism. It doesn't have the concept, that will be difficult for a human to understand that what is really happening here is something. It's something that, for instance, I can use that, but I'm for sure it's going to put a comment here because I'm sure that someone that reads that in 1 month, it's not going to understand. EA doesn't have that kind of thinking, and so you just use that trick or that thing, and it's so. I think if you think about this idea of AI generating code, I think it's even more important for the language to be simple, to be understandable, for you to be able to really understand that the code that you are seeing does what you think it should do. You really understand what the code is doing. So this thing about simplicity, I think it's very important. And I think the other parts from the maybe I may facilitate documentation. I'm not sure if I mean this thing about conceptual integrity, for instance, to keep things that makes sense, etc. I really think that one of the main costs is that it's the burden you put on the user to learn one more thing about your language. So there's the other cost of it. I have said that implementation is the part that AI can really help you. It's not a really important cost.
If you think about like a spectrum of simple to complex, what programming languages are, the most simple ones that you think of, that are easy to understand, less confusing side effects? And what programming languages are the most complex and have the most foot guns?
This famous quote also, I don't know from whom, that the simplest possible, but not simpler than that. Because if you go to the extreme of simplicity, you could get, for instance, lambda calculus or Turing machines and said, oh, that's really simple. I mean, this is really simple, but it's completely impossible to write any program in that. I mean, if you have really simple stuff, I think the extremes will be like that, but you don't want to be there. But to the other side, I think C++, I think, is a good example of a language that I think it's really, really complex.
A question that comes up a lot is, given how much AI has been progressing, would you still recommend people learn computer science today?
If you really think about that, it's really difficult to recommend people learning anything for a profession. I mean, we have no idea what AI will do in 5 years. If someone is entering university now, they are going to graduate in 4 years, 5 years, or at minimum 3.5 years, or then nobody have any idea what the world is, your profession will be like in 4 years from now. So it's really hard to say, oh yes, you're still going to, because now people say, oh no, the manual tasks, the AI is very good, but still need the whole architecture. You need like a software engineer to see the big picture, etc. That it's now, but you have no idea that will be true in 4 years or 5 years. So I think, I enjoy programming. I could do, some people say, oh, use AI for that. I program because I like that. But so if choose something that you like, but really if you're really thinking, how am I going to live with that? I have no idea. It's really, I think it's a really hard time to be choosing the profession.
I mean, you've worked on Lua for such a long time. When you look back on it, what went well and what didn't go well?
We had this privilege of not having to satisfy clients. So we do not have, as I said, for instance, you can choose to add some feature to the language because you do not have a pressure. Oh, we need that feature, whatever it takes, or etc. So we have this privilege of, oh, we are not sure whether to put that. We don't put that. We can wait 1 year or so. I think that it's much easier to do a good project, a beautiful project. So I'm not sure this is a recommendation. Try to work without much pressure. People usually do not have this choice.
What was your measure of success if you're working on a programming language? Like, how did you know it was good?
It's more important to me sometimes that good people that I recognize as like the result than a lot of people that I have no idea who they are, etc. So I think this metric of quantity, that is the standard metric nowadays in the web, it's got much worse, that everything is just in the number of follows. Doesn't care who is following you, just as many people as possible. So sometimes for me, it's much more important if someone that I really admire or think or this, that say something good about Lua, then, oh, we have that many. But of course, it's good also to have some number of users and to be recognized. But I think it's a balance between all of this.
Do you recommend people study other programming languages to get better at programming? And so question is, what are the top 3 programming languages that you think every engineer should learn in 2026 to kind of become better at programming?
Haskell, I think, is an incredible language. It has everything you need to really learn about functional programming. I think one of the main benefits is there is an old joke in the Haskell community that if you write a program in Haskell and in C we'll spend 1 week to make it efficient, and then you will spend 1 year to make it correct. In Haskell, you spend 1 week to make it correct, and then you may spend 1 year to make it efficient. Again, that's not my joke, but it has some truths, not always true, etc. But I think it gives the idea. I think this is maybe the most important lesson of Haskell. But Haskell has many other this thing about type inference, for instance, that in the entire language types are optional everywhere, and yet it can do type inference for everything. It can infer the types correctly, etc. C or some low language. I mean, you can also have to learn some assembler, or to see. But assemblers now are becoming too much complex. It would be to learn like the 8080 assembler, very old assembler but to have this idea of what a machine does, how it does stuff at exactly the basic level, to have this understanding. 𝗀𝗏 is a language that I like very much because of this economy of ideas. Very few concepts, and it can do some amazing things with very few concepts. One language that this is very, very, very old, but I still think it is Snowball. I think one of the first languages to have pattern matching and this idea of doing, it's really strong patterns, etc. And I think sometimes it's interesting to see old languages because exactly nowadays a lot of languages tend to, like I said, the zero indexing, that people, they copy a lot. They tend to be too uniform in some aspects, and so it's interesting to see some older languages that have some ideas that maybe not even good ideas, but it's really interesting.
Last question for you is, knowing everything you know now, if you could go back to when you had just started your career and give yourself some advice, what would you say?
To know a lot of stuff, you really have to study a lot of stuff. It takes time. I also joke about that. People say, oh, learn Lua in 30 minutes or learn Python in 5 minutes, and I always say that they wanted to learn programming in 5 years. That's really take your time. You have to learn that and that. There is a lot of stuff to learn. There is no magic. You really have to learn. A lot of different things.
Thank you so much for your time, Professor. I really appreciate it. It was a lot of fun.
Thank you. It's my pleasure.
Hey, thank you for watching this podcast. If you liked it and you want to see the show grow, please support with a comment or a like. Also, if you have any recommendations for people you want me to bring on, please drop a comment. Guests like Barbara Liskov, Mike Stonebreaker, Mark Brooker, these were all people that I brought on because someone left a comment. On another note, aside from the podcast, I'm working on building the ergonomic keyboard that I wish existed. Here's a glance at the prototype. It's a split keyboard, so there's two sides. This is in the case. But yeah, we launched on Kickstarter and we hit our goal within 8 hours of launching. I really appreciate it if you were one of the people who grabbed one of the early units. We're now working on the long journey of building the tooling now. And so if you still want to pick one up, I've left the late pledges open on Kickstarter, so you can grab one there. I'll put a link in the description. Thank you again for watching the podcast, and I'll see you in the next episode.